Everyone, in my last video, I was discussing the conservation of energy with the help of a simple pendulum. And there I have said you that this is a very simple example to understand that conservation of energy work indeed very well, with very great precision. But accidentally the video got cut, and this part, the analysis, that how it works, how this example, the simple pendulum example, demonstrate the conservation of energy very well. This part was not discussed in that video, and that's why I am here to discuss this part, especially this part. And we will simply retrieve some of the data from that video so that we could only discuss here this thing. See, in the last video I have said you that there's a pendulum and we will lift it up to a desired height and then we'll drop it from here gently. That we have actually done there. And this point was our reference point for the potential energy. So the potential energy here at this level is 0, and at here it is mgh. Wait for a moment. Let's see. Our reference point for potential energy was level this, where the pendulum remains at rest initially, and we will lift up to this, up to the pendulum at a point h, at a point A, which is at a distance h from this bottom line, and we have dropped it gently from there, and then it will go like this. That was our discussion in the last video. You can visit there and see it. See, our potential energy at point A and at point C was mgh. These are the data from last video. And to help it understand better, we need some numerical values so that you can exactly get the how it works. See, let this mass m is 1 kg and this height h is 1 meter. Then the potential energy at A is equal to mgh. As we all know that g is the acceleration due to gravity near the Earth's surface, and its value is, its precise value is 9.8 meters per second square. So what is our UA? Our UA is simply, since it's mgh, it's going to be 1 into 1, and this means 9.8 joule. This is the dimension of energy. Sorry, it's the unit of energy. And this is also equals to the potential energy at C. This amount of energy we have given to the pendulum bob when we have lifted it here. And we dropped it gently so that the velocity here is 0, the initial velocity. So initially the system has this energy. This pendulum has this amount of energy, 9.8 joule. And what I am saying you here is that at every point around its path, this pendulum, this bob, will have this only this amount of energy, 9.8 joule. It will not be 9.9 joule anywhere. It's so precise that it will not increase even a little bit, even in decimal amounts. It will always remain at 9.8 joule. Yeah, it can transfer its form. Like here it's completely potential form. At this bottom point it will be completely in the kinetic form. The energy will be completely the kinetic energy. And anywhere in between the way, if you take this point, then anywhere in between the way, it is a combination of the kinetic plus potential energy. But the total number of the energy, or the total quantity that is available for the pendulum from this pad to this pad, will precisely remain at 9.8 joule. It will not increase up to 9.9 joule, and it will not decrease also from 9.8 joule. See, what is the kinetic energy at B? It will be half mvb square. Since this and this will be equal, as we know, our energy is equals to kinetic plus potential energy at any point. So this is going to fix. EA is equals to UA, since K is equals to 0, and EC is equals to UC, since KC is equals to 0, and EB is equals to KB, because at this point the total energy turns to kinetic energy, since we have taken our reference point for potential energy to be 0 here, since UB is equals to 0. See, there's a little bit, we need to wipe it a little. So it turns out that, our KB is simply by the formula half m VB square. This will be exactly 9.8 joule, because at everywhere to the path the total energy remains this. So equate it, 9.8.2 mVB square. By calculating, you get the VB is equals to root under 19.6, and this turns to be 4.3. Actually, its exact value is 4.4272, but you can take it 4.3 up to two significant limits. Pause it for a moment. See, we have got the speed at the point B as 4.3 meters per second. And our height here, the initial height from where we have dropped it, is 1 meter. What I am trying to tell you is that when you do this experiment in your home, or maybe somewhere with your own hands, then you can see that with this amount of data, means you take 1 kg of mass and this height, then you will see that how many times it swings from this side to this side. This height, which is 1 meter initially, this is not going to increase. Means it is not going to increase even by, this height is not going to be even 1.1 meter, or maybe 1.0001. Means in this height there will not be any infinitesimal increase, even an infinitesimal increase. You can watch it here. You can put a scale here near this point A. While doing the experiment, you can fix a scale here, and then you can measure, you can take the measurement, and you will find that every time it goes here and comes here, it will never ever reach the height greater than this meter. And similarly, if you can fix a speedometer here or maybe on the ball, so that you can measure its speed when it crosses this point, the B point, you will see that it is also not increasing even a little bit extra. VB is always going to remain 4.3 meters per second. It will not be 4.4 or 4.3 to 4, means it will not increase even a fractional increase in this will not happen. It will remain exactly this, and the height will remain exactly 1 meter. This will, why it happens? See, the reason that it happens is because when we lifted this ball initially from here to here and we gently dropped it, we let the potential energy stored of this bob and plus earth system, and that potential energy which we have let to store in it, that potential energy can be turned in kinetic energy if it moves, and that potential energy, when it turns kinetic energy, it can deliver the speed this. It has delivered, as we have seen we have calculated here, this speed, which means that if we need some extra speed, if it becomes 4.4 meter per second for a moment, then this 0.1 then this 0.1 increase in this speed, it is coming from nowhere, which means that this 0.1 meter is violating the principle of conservation of energy. As this also says that we cannot have a perpetual motion to anything. Perpetual motion simply means that a motion which starts from nowhere. Here we have given it the potential energy that was 9.8 joule, and this potential energy can generate the velocity of the particle here at 4.3 meters per second. But if we think that it's increasing to 4.4 or more than this, then we must get the extra potential energy from somewhere else. Or maybe if we hit it from here so that it could increase to 4.4 or 4.5 meter, then we are providing this mass the extra energy. Unless we touch it, if we just let it drop initially and let it go by itself, if we do not touch it, then doesn't matter how many times it swings back and forth in this moment, it will never going to increase the height greater than this meter at this point and this point, and the speed greater than this meters per second at this point. This simple example, by doing this, will show you that energy is precisely conserved. Energy is also not going to increase from 9.8 meter. It is going to remain the 9.8 joule at every point of this pendulum. If you take it here, there may be some part has been transferred in kinetic energy and plus potential energy. The added form, take this at x and this point at x dash, then energy at x will be kx plus ux. It will simply be half m bx squared plus mg hx. And at x dash, actually we have taken it x dash, so we'll go with the prefixes x double dash here. It becomes half m v x double dash squared plus mg h x double dash. But every time this sum is going to remain 9.8 joule, is going to remain 9.8 joule. It will not increase from 9.8 joule. Doesn't matter how many times it swings back and forth. And if this experiment is, if we'll do this experiment somewhere in back home, then we'll see that this pendulum goes swinging for a very long time. Even in your home, if you can do it, then you can see that this number of swings are very large. Somewhere near 1,000 swings. I have done it and I have seen that it's somewhere between 900 or 1,000 swings before it stops. Actually, in our room or doing these experiments in our room or lab, the pendulum gets stopped due to the frictional forces which arise from the air molecules to this pendulum, which is actually called the damping in the oscillations. Again, we'll discuss the oscillation and damping in some other videos. But here, what I'm trying to tell you is that the energy reduces and this comes to zero because the energy gets transferred to the air molecules whenever the friction comes in between. But it never gets increased until you provide some extra energy to this system from somewhere else. If you want the speed to increase here or the height to increase here, then you can simply do, whenever it comes here, you can take a little bit push in it here, then probably it has some better speed here, greater speed here, or it will reach some to a greater height up to here. But there you must remember that you have given the extra little bit energy from here. If you do not touch the system, once you drop it gently, after that you do not touch the system, then this system has, the energy of this system will never going to increase at this value. And the velocity is never going to increase at this point from this value, and this height h is never going to increase from this 1 meter. So I have said you that this simple example, you can do it in your home, helps you understand that energy is really conserved.